Hello friends, you are watching ERUDIRE Plus, the professional CAD/CAM solution provider. Let's get started.
Hello viewers, today I'm going to show sloshing effect inside an oil tanker using SolidWorks Flow Solution. We'll not be restricting to only sloshing effect. Together with that, we'll show how to reduce this sloshing effect by using different types of baffles. We'll design different types of baffles and we'll see their efficiency in different cases, right? So before starting this sloshing effect, we should understand what is sloshing effect, right? It is like inertia forces. Actually, when the tanker containing oil suddenly applies a brake, in that case what happens, the oil inside the tank will be having some kind of turbulent motion, or you can say pitching effect will be occurring inside this tank. Excluding pitching effect, some kind of forces will be exerted at the surface walls. That is very dangerous and it can produce some kind of accidents also. So in our analysis, we'll show how this sloshing effect is creating some kind of torque and also pitching effects, forces on the walls. And in the next analysis, by using different design of baffles, we'll reduce this sloshing effect, right? For understanding this one, let us have a segmented view of this model and we can see it in a better way. We can cut it from front end. So the thing is, this is the tank, and this portion, down portion, you can see this part is filled up with crude oil. In our case, we have considered propane, and the top part is filled up with air. When the car starts moving suddenly, or when some kind of brake is applied, in both cases sloshing effect can be seen. Now let us start our analysis. Started the flow simulation, and the flow simulation environment will be initiated with wizard, and we're keeping the name of the project as project 1, and from unit system we're considering SI, and for main parameters we're considering temperature as degrees Celsius, though it is not important criteria, but as per normal practice we're considering this one as Celsius. And next to that, we need to consider what type of analysis it is. It is an internal analysis. And from physical features we need to consider it is a fluid flow, and we are not considering heat transfer, so conduction we will not consider. And inside the tanker it will be heterogeneous mixing of oil and air, so it is a free surface technique and it will be time dependent. It is a transient analysis, so we're considering it is a time dependent analysis, and we're considering analysis time to be 20 seconds. And output time step, we're considering this one as 0.1 seconds. That means after each 0.1 second we will receive the results. Gravity will be involved in this case, and the direction of gravity is y, so along y direction it will be minus 9.81 meter per second square, and along z it will be 0. And one important case in this case, that while the car will be moving, gravity is very important. There will be some kind of dependency. Actually you can see the car is moving in x direction, so along x direction it will be having some kind of dependency. That is, the movement of the car will be determined by this dependency. So we'll make this one as time dependent, and let us make a graph that how the car will be moving, right? This graph will be actually following the movement of the car, right? So the car will be moving according to this graph, right? So at 0 seconds, acceleration of the tanker will be 0 meter per second square. At 1 second, let us consider the acceleration as 1 meter per second square. At 2 seconds, let us consider it is 2 meter per second square. At 3 seconds, it is 5 meter per second square. At 5 seconds, let us consider the acceleration equal to 10 meter per second square. Up to 10 seconds, it will run with the same acceleration of 10 meter per second square. So next 10 seconds also it will be having same acceleration of 10 meter per second square. Next 11 seconds, let us consider it has applied a brake and immediately acceleration has come down to 0. And up to 20 seconds it will follow with the same acceleration of 0, right? Let us consider 20 seconds, acceleration is 0 again. You can see the graph generated. This is a graph. At 0 second, acceleration is 0, and you can see at different times different acceleration, right? So following this graph, the tanker will be moving, right? Let's close it. As I told before, in this tanker there will be heterogeneous mixing of oil and air. In this case we are considering oil as propane, so it will be a free surface technique. Next to that, gases, we're considering gas as air, and liquid, we'll consider liquid will be propane. Next to that, default outer wall thermal conditions and roughness we're considering, and next to that, from thermodynamic parameters, pressure will be 10132 Pascal, and though temperature is not an important criteria in this case, we are considering temperature as 45 degrees centigrade, and concentration initially it will be filled up with air, right? Let us finish it. You can see this is the computational domain. Let us hide this domain. Now first of all, we can see the bottom part of this tanker is filled up with oil or propane. So while modeling this one, we have kept this as solid. Now from initial conditions, this solid to be disabled and that to be converted as oil. That can be done from initial conditions. So starting with conditions and initial condition, let us select that solid component inside this tanker. That can be selected from the geometry itself. It is solid component. Let us select it from here, and this is revolved part, the down part. While designing this one, we have made this solid. Now using initial conditions, we have to make this solid disabled, and instead of this one we have to take this one as propane. Done. So we've considered that down part is filled up with propane and the top part is filled up with air. Initial condition is done. Any other boundary conditions are not needed at this case because we didn't keep any kind of opening. All the exit points we have made it closed, so there is no opening in these cases. And next to that we need to find goals. So all the goals will be actually global goals. We can have a lot of parameters, but our main aim should be to see the sloshing effect and also force and torque. Torque is actually the pitching effect, right? So what we'll see, we will see average dynamic pressure, then you can see things like average turbulent intensity, then you can see things like force and also torque in the y direction. That will be actually causing pitching effect. Green check. We have decided 4 different goals. One is average dynamic pressure, second one is average turbulent intensity, third one is force, and the last one is torque or pitching effect. So our aim should be to reduce that pitching effect or torque. Before running this one, we need to see something else, like from solve we can see calculation control options, and from saving you can select periodic, and from here you can select parameters like immiscible air, immiscible propane, and even volume fraction of air and volume fraction of propane. Okay, done. Next to that you can go for meshing and see what it is. Edit mesh. Let us go for manual meshing and we can check refinement level, display refinement level, and you can see that is up to 1. We can make this refinement level up to 5. Done. Now we can run this one with new calculation. Let us run it. You can see the solver window. It has already started running. These are the different goals we have decided. By the same time, you can see from this plot also settings, you can see mass fraction of propane and from image attribute we can see this one. You can see how it is propagating. This is sloshing effect without having any kind of baffles. That's why you can see huge amount of turbulence is created inside this oil tanker. And you can see here all the results are actually converged, right? Solver is finished and you can see the results are converged. And you can see dynamic pressure is 353.30 Pascal. Average turbulent intensity is 2.23%. And force is 4,33,890 Newton. And torque in this case is 2,246.2 Newton meter. Let us close it. First of all, we'll see the results from here, and with Transient Explorer on, we can view different cut plots of pressure, velocity, etc. Let us make the Transient Explorer on, and you can view it from the front plane. Now, from cut plots, we want to see like immiscible propane. Instead of pressure, you can see immiscible propane. Grain check. So initially you can see this is the level when at the starting point. Let us see the sloshing effect right now. So while the car will be moving from 0 to 20 seconds, it will move in the x direction. By the same time, we can see sloshing effect inside this tanker. Let us see it. So you can see at different times it is different. So after some time it is being stable, right? You can see here perfectly. So the down part is actually propane and the top part is filled up with air. Let us close this one. Next to that, we can hide this one and we can go for surface plots also. Let us clear and hide, and we can see surface plots. Let us insert this surface plot. You can see all faces and grain check. This is the surface plots. It is showing the fraction of propane and air. Top part is filled up with air and bottom part is filled up with propane. It is showing the level at the side walls, or you can say at the surfaces. Let us close this one, clear and hide this one. You can go for ISO surfaces also. Let us insert ISO surface. It will show the interface between this oil and air. This is the interface between oil and air. You can see it at different times, how it will be moving. This is the interface between oil and air, right? At different times it is actually moving. We can see the dynamic behavior of this heterogeneous mixture. At different times you can see its location at different position. Let us clear and hide this one. And goal plots we have already seen. Let us see this one again. Insert goal plots, and we can transfer all this data to Excel to have better representation. Let us export to Excel. First one is the torque. We can see very high torque is there. You can see in the upside, positive side, maximum torque is 2 meganewton meter, and downside you can see it is approximately 1.5 meganewton meter, right? This torque is very high, so that torque can be reduced by using different types of baffles. The design of different types of baffles also will be shown in different analysis in the next cases, right? Next we'll see the force. After 214 numbers of iterations, you can see maximum force is actually 1.9 meganewton. Next one you can see average turbulent intensity. Initially turbulence is very high, and after 300 numbers of iteration it just come down to low level. Next one you can see average dynamic pressure. You can see maximum dynamic pressure is actually 0.94 megapascal. So these are the results we got from the sloshing effect without applying any kind of baffles. Next to that, we'll change the design. Instead of this normal design, we'll make some kind of baffles and see how this sloshing effect can be reduced, right? For that, we need to go to the model and make the design a little bit changed. Let us see the model and we can start drawing from the front plane. This is the central line of this tanker. You can make some lines, solid lines from here, the middle point, and we can put smart dimension to this one. Total length is 4000 millimeter, and up and down it will be same. So from downside it will be actually 2000 millimeter, and up also it will be 2000 millimeter, right? I can do one thing, these two will be actually coinciding, right? Done. We made this line. Now we have to make offset lines in both direction at a distance of 1000 millimeter. So let us select that line and offset entities bidirectional. We can make the distance to be 1000 millimeter. Again, offset entities and it will be 2000 millimeter. Done. This way we have to make some lines in both sides. Again, we can repeat this one. Offset entities, it will be 3000 millimeter. Grain check. We can repeat this one up to 5000. Offset entities 4000 millimeter. Done. Now the final one can be offset up to distance of 5000 millimeter. So on both sides we have made some kind of special lines, normal lines, and with this line we can make some kind of baffles on both sides, right? For that, what we'll do is we cut this model in a different plane. Let us cut it from different planes and cut it from this right plane, and we have to make these lines as baffles. So what we'll do is we can select those lines and that can be extruded, extrude boss base. Instead of blind, you can make it up to surface. You can make it up to this surface. Done. Again, we can do another thing, like we can others direction also we can change it. Direction 2. Instead of blind, you can make it up to surface. Done. Green check. So the baffles are made. You can see it. If we change the cutting plane, then you can view it in a better way. From top plane, you can cut it and see the baffles. Right. So these are the baffles. We have provided the baffles at a distance of 1 meter. Right. Now with these baffles, the turbulency or pitching effect, even the forces also can be reduced. Right. Let us go back to a previous model. We can make a clone of this one. Now in the project 2, we have cloned all the previous boundary conditions and we have only added these baffles to reduce the sloshing effect or to reduce the pitching effect due to sloshing, right? So let us run it with new calculations, and we are running this one for 20 seconds. Let us see the solver window. You can see now in this case, as we have provided some kind of baffles, so pitching effect is being reduced, and by the same time forces acting on the surface of this oil tanker will be also reduced. You can clearly see this from the solver window. The goal parameters also you can check it. All the goals are actually almost converged, and To that you can see the sloshing effect inside this oil tanker. Let the iterations move on. As time is approaching, you can see result is varying. Solver is finished and you can see the results are converged. And here in this case, the data we are getting all are actually average one. First one is average dynamic pressure, it is 133.403 Pascal, and second case is average turbulent intensity is 5.846, and third one is average force, it is 0.43 mega Newton. Average torque, you can see it is 2814.65 Newton meter. This is average torque. In our analysis, average torque is not that much of importance. Our importance should be given on the maximum torque and minimum torque, etc. We have to see the maximum and minimum values that can be viewed from the goal plots itself, right? Now we can close it and we can see the results. And in this case, our main aim is to see that sloshing effect only. And before that, you can go for this Transient Explorer and you can view this one from front plane. So cut plots, insert cut plots, and we're going to see sloshing effect. It will be immiscible propane. Let us view it. You can see by the application of these baffles, the sloshing effect is minimized, and you can see that pitching effect, or you can say torque, is also minimized. We cannot see that much of rise inside this tanker, so it is minimized, right? This is a second design. Next to that, we will go for some other design and we'll see how this sloshing effect will be minimized. And at last, we'll compare all these results and see which one is more important, which is more efficient one, right? Our aim is to see that whether sloshing effect is reduced or not, and with which design the sloshing effect will be minimum, that to be seen. Let us clear and hide this one. Next one, we'll clone this project and we'll keep all the boundary conditions exactly same like the previous one, and we'll change the baffle design little bit different way, right? So for baffle design, what we'll do, we have to go for the model again. Suppose we are considering this one or right plane, anything. On that plane, we need to draw something. So this one is a different design on the baffle. We can have different types of design, and after comparing all these things, we'll see which one is better one, right? So let's draw something on this plane. Made a circle and let us provide some smart dimension to this one as 1500 millimeter. Done. Next one, we can cut this one. Actually, we want to make a central hole at the surface of these baffles, so we can cut it. Features, extrude cut, and that can be cut up to surface. To see up to the back surface only. Done. One central hole is created at the central baffle. You can see it in a different way. Let us see it. Yes, this hole is clearly visible. Now the thing is, if we do some method like a linear pattern, in that case we will not get the actual design, because the thing is, if we provide linear pattern, the downward wall portion also will be cut. So to avoid that one, we will do something else. We will copy this sketch to different baffles and cut it separately, right? Let us take the second plane, then sketch. From the previous drawing, we can go for convert entities. Excluding that one also, we are having some other options also, but this one is easier. Features, extrude cut, and that will be cut up to the back surface. Select that surface, it is cut, grade check. So we got two central holes on these baffles, right? You can see this is a hole, right? Now the third one is required. By this same way, you can make all the holes at the different baffles, right? Let us proceed. So we got our new design with all the baffles with central hole, right? So with this different design, let us see how the sloshing effect will be reduced or increased. That one can be viewed, right? After viewing all these things, we have to compare their results. Let us run this one with the same boundary conditions as we have cloned the previous boundary conditions, so we can run it with a different design, right? Let us run it with new calculations, and we can see the solver window. You can see the results together with the sloshing effect inside this oil tanker. This is a different design. In this case, you can see that pressure pulsation, or you can say sloshing effect, is also minimum. But I think the second one was better one, because sloshing effect is there, but the thing is that pitching effect is not that much of reduced. And whatever goal plots we are having here, these are actually average values. So in this case, maximum important is actually torque or pitching effect. So we have to see the maximum or minimum torque effect that can be viewed from the goal plots itself. Excluding dynamic pressure, all actually converged. Let us see how this is going on. All the results are almost converged. It is clear that sloshing effect is less in the previous case. As you can see, the down part is filled up with propane and the top part is filled up with air, and in between we are having the interface between propane and air. Solver is finished, and you can see all the results are converged, indicating with green color, right? You can see here average dynamic pressure is 130.261 Pascal, average turbulent intensity is 6.128%, and average force is 0.436 meganewton, and average torque is 572.389 Newton meter. Right, these are average values, but we need to see our maximum and minimum one also, right? So let us close it, and we need to see results. First of all, we need to see from the Transient Explorer itself, and for better view we can see from front plane or front view. Cut plots, insert cut plots, and we want to see immiscible propane, grain check. Let us see how this propane is moving inside this oil tanker through the Transient Explorer, right? So this is a good design, but compared to the previous one, it is not that much. And this is just visualization, and to compare all these results, we need to see the actual results, right? Let us close it and can clear and hide these things. Next to that, we want to compare all these results. The previous 3 different projects we need to compare. Transient Explorer is off. Now let us compare the results. We're considering project 1, 2, 3. In project 1 is actually without baffles. Project 2 is a baffle without hole, and project 3 is baffle with a central hole. Let us compare all the goal plots. We can compare the cut plots also. We have already seen the cut plots, better to see the goal plots. Now these things can be seen a better way in the form of graph. First of all, see average dynamic pressure in project number 3, it is 130.226, and in project 1 with no baffles, average dynamic pressure was 353, and with project 2, average dynamic pressure is 133.4. That means with the baffle with central hole, we can see the dynamic pressure is little bit less compared to the others, right? And second one, we can see turbulent intensity. With the project 3 with the baffle at the center hole, turbulent intensity is more, and without doing any baffle, the turbulent intensity is minimum 1. And similarly for the forces, we can see almost all cases you can see similar amount of force was exerted on the walls. And the last one, the most important part, we can see the average torque. Average torque is minimum in project 3 when we have provided baffles with a central hole, and project 2 that average torque is more. It is 2814.653 Newton meter, and project 1 without baffles it is 2246.223 Newton meter. These are actually average values, but we need to see the maximum and minimum values of these torques, right? That can be viewed from the graphs, and you can see it from this summary history. Let us see this one in a better way. So you can see 3 different projects. Green color is actually project number 2, baffle without central hole. Project 1 is without baffle, and project 3 is baffle with the central hole. First one is actually dynamic pressure. We are not bothered about that one. Second one is turbulent intensity. Most important part is to see the torque, that is the pitching effect. So you can see here project 1, the torque is maximum, that is pitching effect is maximum. It is actually, you can see it is after 96 numbers of iterations, you can see it is 2101 mega Newton meter. This is very high. Minimum is actually 1.5 mega Newton. So pitching effect is very high in case of the first case when there was no baffle, right? You can see this is the pitching effect, and project 3 is a red color. So in that case also you can see that torque is very high. Minimum torque is actually approximately 1.5 mega Newton meter, and in the project 2 it is least one. That means when we have provided the baffle with no hole, in that case sloshing effect was minimum, even the pitching effect is also minimum. So if we see the pitching effect, maximum pitching effect is visible in case of project 1 without baffle, and minimum pitching effect is visible in project 2 when we have provided a baffle without central hole. And again, based on our requirements, sometimes we may be more concerned about dynamic pressure. In that case also results will be different. Okay, we can transfer all this data to Excel also. First one is torque. So these graphs can be seen in a better way. This is the torque one. This is the most important part. Project 1 is without any baffle. Torque is maximum. It is actually highest torque is actually 2.1 mega Newton meter, and minimum torque is actually 1.5 mega Newton meter. In project 1 when we have applied no baffle. Project number 2, that is green color, we can see it is minimum 1. It is almost streamlined. So pitching effect is almost minimized. No pitching effect is there. Sloshing effect is minimized in project number 2 with the baffle without any central hole. And third project, you can see here, third project is actually red color. In that case also minimum torque is in the range of 1.2 mega Newton meter. That is also not good enough. But in that case, in project number 3, other parameters may be minimum, but we have to be concerned about maximum or minimum pitching effect. So from this data, we can see some other things also. Forces also can be seen. Almost all cases forces are equal, and turbulence intensity is also almost equal in all cases. This is average dynamic pressure. Average dynamic pressure is very high in case of project number 3. And project number 2, dynamic pressure is very less. It is almost streamlined. So these are the things. So from this analysis we could see that sloshing effect is very dangerous. It can produce any kind of accident, and that sloshing effect can be reduced by applying some kind of baffles. And different types of baffles may be there, and we can optimize these baffles, changing the dimensions of all these things or changing the design. We can optimize these baffles and we can reduce this sloshing effect, right? So with this one we'll conclude our today's analysis. This was a very simple analysis, and it is actually used in oil fields, right? Thank you so much for watching this video. Thank you again. Bye. If you like this video, please subscribe and share. And if you have any kind of doubts, please write to me. Thank you so much for watching this video. Thank you again. Bye.